So our next speaker is Sumitra Ganesh from JP Morgan. Sumitra leads the multi-agent learning and simulation group at JP Morgan AI Research. The simulation platform developed by her team based on RL is used across multiple use cases, including, but not limited to, market simulation, operational processes, consumer loan markets, and much more. And she uses these things for counterfactual analysis and strategy optimization. Sumitra has a PhD in electrical engineering and computer sciences, also from UC Berkeley. And today she'll be presenting how RL can be used to solve two primary challenges in agent-based modeling. The two are finding the equilibrium with multiple strategic agents and calibrating the model using real data, and how these techniques have been useful in enabling the practical application of agent-based modeling at JP Morgan.
Very cool. I'm excited to learn more, and welcome, Sumitra.
Welcome.
Thank you. Thank you for the introduction. So as mentioned in the intro, I will be talking about RL-based simulation of markets, but much of what I have to say applies really not just to financial markets, but markets in the broader sense of the term, things like ride-sharing markets or other complex multi-agent systems. So every RL talk has to start with a picture like this. So in theory, the way you train your RL agent is that your agent takes actions. The environment then responds with some observations and rewards. And the agent then uses your favorite RL algorithm to improve its policy using this stream of experience and maximize its long-term expected rewards. Now, in practice, it is typically too expensive and risky to train your RL agent in an interactive manner like this in a real-world environment. So in practice, most RL agents are actually trained in simulation. And this simulator could be, for instance, a physics-based simulator like Mojoko in a robotics application. But what I'm going to talk about today is domains where your environment is made up of multiple other agents. And these agents might have policies of their own. So the question then is, how do you model the system of interacting agents? And that's going to be the focus of my talk. So let me motivate this with a very simple example of a market. Say you're in the business of selling printer paper. And this market is made up of 2 other shops that also sell paper and compete with you, and 3 customers, Alice, Bob, and Carl. Each of the shops has to decide at what price they want to sell paper, and they have to manage their inventory. And the customers have to each decide whether they want to buy paper, how much paper to buy, and from which shop. Now, no real-world market is quite so homogeneous. For one, different customers could have different preferences on cost versus delivery time. So for instance, Alice might be someone who is optimizing for cost and is willing to wait longer to receive her paper. Whereas Carl might be someone who wants his paper tomorrow and is willing to pay more for it. Similarly, shops could have different storage costs, and that would in turn constrain the way they could price and how much inventory they would carry. And as you can see in this graph here, the agents could have different levels of connectivity to each other. And that influences how much information an agent has access to. For instance, Alice here is connected to all 3 shops, so she sees prices from all 3 shops, whereas Carl is only connected to 1 shop. And much of the dynamics of complex real-world systems really arises from this heterogeneity of agents and how that interplays with the interactions of these agents. So this heterogeneity is a very important thing to capture when you're modeling real-world systems. Now let's do a simple thought experiment. Let's say you control shop Z, and you're interested in evaluating what would happen if you changed your pricing policy. So you'd like to evaluate how that change would impact your sales, revenue, and market share. Now, the answer to this question is it really depends. It depends on how Alice and Bob, the customers you are connected to, change their buying behavior in response. And that in turn depends on what type of customers Alice and Bob are, what their preferences are. And it also depends on what are the other options, what are the competitors that they are connected to. So the impact also depends on how your competitors change their pricing policy. So all in all, this is to say that answering this question really requires simulating how other agents in the system change their behavior in response. So how do you simulate that? And that's primarily what I'm going to talk about, is the approach that we have developed in my team to use RL to build agent-based simulators. So there are primarily three questions that you need to answer to build an agent-based simulation. The first is, how do agents differ from each other? That is, how do you specify this heterogeneity of agents? And we use reward functions and the connectivity graph between agents to do that. The second question is, how do agents behave? How do you specify behaviors? And how do these behaviors evolve? And RL here is a really natural tool to automatically learn agent behaviors and policies. The third question then is, how do you even know what types of agents are present in the system? Because clearly the dynamics of the system depends pretty heavily on this. And here I will talk about our work that we published a couple of years back on using RL to calibrate the agent composition using real data. And that makes this set of simulation techniques very powerful for applications. So let me dive in with the first question of how do you specify heterogeneity of agents. So as I mentioned, one way in which agents are different from each other is they have different levels of connectivity. And you can specify this, as we do in our framework, using a deterministic or stochastic network between agents. The second aspect in which agents differ is that they make different trade-offs because of differences in preferences and constraints. And this we encode into the reward function for agents. To make this more concrete, let's go back to the shop and customer example from before. So let's say in the printer paper market, every shop cares about three things: maximizing sales revenue, minimizing storage cost, and minimizing the shortfall between their inventory and demand. Now, while every shop might care about these three terms, they might care about it to varying degrees. And you could capture that variation by assigning different weights to these terms in the reward function. So every shop has the same form for the reward function, but different weights. And you can get different types of shops by specifying these weights. And the combination of these weights in the reward function and the connectivity parameters are together referred to as the type parameters for the agent. And you could do a very similar thing for the customer. Now I'm going to take this simple printer paper market and extend that into a financial market in a single asset. So let's say it's IBM stock. This market consists of two types of players. There are market makers and investors, similar to the shops and customers in our previous example. Market makers have to decide at what prices they're willing to buy and sell stock, and they have to manage their inventory. Investors have to decide whether to buy, sell, or do nothing. But there are two key differences. In this market, all agents can both buy and sell stock. So they can transact in both directions. And every agent has an inventory, and that inventory can also be negative. It simply means that they are short the stock. The second key difference is that the value of the inventory can fluctuate with time. And that is because the value depends on the reference price for the asset at the exchange. And this kind of fluctuation gives rise to what we call inventory profit and loss, or inventory P&L. And of course, you hope it's more profits than loss. And it also gives rise to risk that comes from the uncertainty of the value of the inventory. So similar to what we did with shops and customers, we can set up the reward functions for market makers and investors by specifying the terms of the reward function and then letting each agent put different weights on these terms. So what do market makers care about? Market makers care about maximizing their sales revenue and maybe meeting some market share target. Crucially, they care about minimizing risk from inventory. And you could have market makers that are more risk averse and place a high weight on this risk term in the reward function. And then there might be others who are less risk averse. Similarly, you could have different types of investors. So let's say Alice is a day trader and she cares about maximizing her inventory P&L and minimizing her execution cost. And she doesn't care much about risk and meeting some quantity target. Whereas Carl might be a long-term investor, and he cares primarily about executing some target quantity. He has identified, say, 100 shares of IBM. And he's identified this target based on his investment thesis. And that's what he primarily cares about. He cares much less about the shorter term inventory P&L and execution cost. So now that we have set up reward functions for the agents in this market and ways to specify different types of agents with these weightings, we are really all set to use RL to learn policies for these agents. Now, one way we could do this is to learn a separate policy for each agent. After all, I have been telling you how they are different from each other. And we could use this by using each agent's experience, that is the stream of states, actions, and rewards, or observations, actions, and rewards it sees, to update its policy. The issue with this is that it is hard to scale as the number of agents increases. It is also unstable in its learning dynamics. And importantly, it doesn't really leverage any of the commonality across agents. So just because one market maker places a slightly higher weight on the risk term in the reward function doesn't mean that its policy is entirely different from that of other market makers. In our work, we leverage this commonality to make the learning more efficient using what we call a shared policy learning approach. In this approach, we learn a common shared policy across, say, all the market makers. And this policy pie takes as input not just the observations of the agent, but also the agent's type parameters, lambda. And as I mentioned previously, lambda could be the weights the agent places in the reward function, as well as its connectivity parameters. The policy, this shared policy, is then trained with the experiences of all the agents. And you could do this using a policy gradient method like PPO, which is what we use. And the main difference here is that you also plug in the type parameters of the agents as you're doing the updates. The advantage of this approach is that we are able to learn a shared policy that generalizes across the different types of agents. And it is more efficient because it leverages parameter sharing and the experiences of all the agents to do the updates and learn faster and in a more stable way. So let's take a look at what this means for the RL-based investor. In this simple illustrative example that I have here, we set a quantity target of 75% buys and 25% sells for all the investors. So every investor is essentially making a trade-off between meeting this quantity target and maximizing its P&L. And we place a weight of W here, denotes the weight on the P&L term in the reward function. And after training the shared policy, what we've done here is do rollouts with the shared policy, plugging in different values for this weight. And this is really to explore and understand what the shared policy has learned for different types of investors. The blue line that you see in this plot is the reference price for the asset. And you can see when we set a weight of 0 for P&L, the shared policy is largely trying to meet the quantity targets. So it ends up buying most of the time. The buys are denoted by these green dots here. And it sells about 25% of the time. But you can see it's not being very strategic about how it times these trades. it buys even when the price is high. But as you increase the weight, it starts to time the trades in a more careful manner. It's still, for a weight of 0.25, it is still trying to meet the quantity targets, but it is now buying when the price is low and selling when the price is high. And as the weight increases further, it completely ignores the quantity target, and you start to see opportunistic buying and selling behavior to maximize P&L. So what's really cool about this is that you can simulate and generate a whole range of behaviors using a single policy. And you can do that simply by varying the type parameters for the agents. We see a similar thing for the RL-based market maker. The RL-based market maker learns to do what we call price queuing, but in simpler words, it's just that the market maker learns to sell at a discount whenever it has a very large inventory. So because the market maker is both buying and selling, what you can see in the top plot here is when the inventory is large and positive, it learns to set a more favorable sell price versus buy price. But what is really interesting is that the shared policy also learns to modulate this behavior and vary the intensity of this behavior depending on the market maker's risk aversion and connectivity parameters. So the shared policy learns to skew more aggressively, to do this discounting more aggressively, if the market maker is more risk averse or less connected, which makes sense because in both of these cases, the market maker has to be fairly aggressive to manage the inventory. So now that we have set up different types of agents using the reward function, and we have also managed to scalably learn a range of behaviors corresponding to agents of different types, the question still remains, how do we know what types of agents are present in the market? And ideally, we want to be able to calibrate the proportions of different types of agents in the system using real data. So the way this could work, roughly as a sketch, is that you have a calibration algorithm that picks the agent composition and essentially sets the proportions of different types of agents in the simulation. These RL agents then learn and reach some equilibrium. And then you collect data, simulated data, and compare it to real data, calculate some calibration loss. And then this calibration loss is used by the algorithm to pick the next agent composition. And this calibration algorithm could be something like Bayesian optimization, for instance. The issue with this is that it is quite slow because for every single setting of this agent composition that you're going to try, in the inner loop, you have an RL training process where the agents have to learn and, in an ideal world, converge to an equilibrium before you can calculate the calibration loss. What we proposed instead in our paper, this was NeurIPS 20, is to use an RL-based calibrator agent. And this RL-based calibrator agent, its actions are to pick the next agent composition, and it receives rewards based on the calibration loss. But the really nice thing that we can do here is to adopt a 2x scale approach, which is that the calibrator learns and picks agent compositions at a slower pace than the agents in the simulation. So the agents in the simulation are able to adapt their policy to the new agent composition. And so we are able to learn both the agent composition corresponding to the real data, as well as the behaviors and policies of the agents in the simulation simultaneously. So in one shot, we can learn both of these things and be done. We've been able to use this method very successfully, actually, to calibrate market simulators using real foreign exchange market data. What you see here in this plot is the relationship between the flow that a market maker receives in this market versus the pricing on the x-axis. And this relationship, the blue curve here is extracted from actual market data, and that is the target that we want to match. The orange curve is what we're able to achieve the fit we are able to achieve with RL-based calibration, the method I just described. And what you see in green is the fit achieved by Bayesian optimization. And as you can see, we are able to achieve a far better fit than Bayesian optimization. And this is true for the market share targets as well. So to conclude, I think RL-based simulation of complex multi-agent systems is a very powerful technique and has a huge amount of potential, even outside of financial markets, as I said at the beginning of my talk. In particular, using RL to automatically learn agent behaviors and to learn the agent, calibrate the agent composition, really opens up the possibilities for applications, because these are the two things that are often time-consuming and very domain-specific when you're trying to build agent-based models. What we've done on my team is to build a framework called Phantom for RL-driven multi-agent simulations. This actually uses Ray RL-lib out of the box, and we've been using RL-lib for the past 3 years, actually, pretty extensively in our work. So if you're interested in using this framework or talking about further applications of this kind of RL-driven simulations, I'd be more than happy to chat. You can send me an email. Also, if you want further details on the techniques I spoke about, you can refer to our publications. I have them listed here as well. Thank you so much for your time.
Awesome. Thank you so much, Sumitra. It's great to see reinforcement learning at one of the top financial institutions in the world. And I loved seeing Phantom as well. I've been doing some scraping through GitHub repos to kind of understand how RL is being applied in the finance space in particular. And this is another excellent framework to check out. So we do have time for a couple of questions. If you don't mind, I would like to sort of share them with you, and so that you can give your response to the audience.
Yeah, sure.
Excellent, cool. So question one, do you have any existing research on encoding behavioral biases into the multi-agents as a relaxation of rational behavior?
Yeah, that's a great question. Yeah, so that is an assumption we make here, that the agents are perfectly rational with respect to their reward functions. We, in our work, we don't have publications on this, but in our work, we actually have the ability in our framework to specify both hand-coded strategies as well as these RL-learned strategies. So that's typically how we do a mix of these types of agents. So you might have smarter agents and less kind of agents with more defined behaviors that are not evolving. But I think it's actually a very interesting open area of research to say, what if you want to have, how do you, in a systematic way, learn bounded rational behaviors? So I think that's an interesting topic of research.
Awesome. And how can we tell the model is learning from the structure of the problem? How is it learning the structure of the problem rather than picking up from history that it might have observed previously?
Actually, in an agent-based model, based on how you specify agents, you are putting a lot of structure into the model. Yep. So essentially, you can think of it as a very structural model with which you are using historical data, as you'll see, only to calibrate what types of agents exist in the market, right? So it is, the idea is that what we want to do here is counterfactual simulation. So what we want to extract from historical data is only sort of what are the different types of agents with their preferences and constraints, and then that's the only thing we really want to extract from the historical data. Because when you put in a counterfactual scenario, you then want to say, how would these agents of these types now react, and what type of new equilibrium will they reach with this change? So it is very, I would say, highly structured and very parsimonious in its use of historical data.
Excellent. Sort of selfishly, I have a question. At the beginning of your presentation, you mentioned that JP Morgan Chase is using RLib and Ray in a variety of ways, for market simulation, operational processes, consumer loan markets. Which use cases do you find require scale more than others?
I think so. We've been using RLib, let me say, for 3 years now. So thanks to the RLib team who actually helped us get set up. Most of this is fairly intensive because what we're doing with simulations is fairly intensive most of the time. I would say the OTC market simulation, which is the FX market example that I gave, is probably the biggest use case that we have in terms of scale. But there are other consumer markets which are actually even larger in scale that we are exploring now. So it has been a huge benefit to frankly keep that to start from that base and from that infrastructure to begin with.
Excellent. And do you think we have time for one more question?
Maybe let's do one last one.
Excellent. So the final question, someone said, thanks, Sumitra, great work. Have you compared your approach to bandit policy, and is your approach adaptive?
Sorry, I didn't fully get the question. The approach for what, the simulation?
The question was, have you compared your approach to bandit policy?
Bandits.
Okay.
When you're learning.
Yeah. So I guess I'm going to interpret the question as, what if you use bandits instead of RL in learning behaviors? We haven't, primarily because a lot of the use cases we are looking at require some longer term behaviors and state carried forward. So we haven't looked at bandits as an alternative to RL there.
Gotcha. Excellent. Well, thank you so much for your time. I can't wait to read more about Phantom and about the other publications that your team has produced. And I think we're headed into a break. Is that right?